What happens to a tire after it can no longer safely roll down the road? In this facility, the answer begins with an enormous mountain of discarded rubber. Tires that once carried cars, trucks, and motorcycles are about to enter a completely different life. Instead of becoming waste, their rubber, steel, and fibers will be separated and processed into useful materials. The transformation looks almost impossible at first. A complete tire is too large, too complex, and too strong to simply press into a block. First, the tire has to be dismantled mechanically. Its steel reinforcement must be removed. Its textile fibers must be separated. And its rubber must be reduced to carefully controlled particle sizes. The finished product can take several forms, but this documentary follows a generic recycled rubber paving block. Depending on its formulation and design, this type of material can be used for surfaces, walkways, protective flooring, and other applications where resilient rubber is useful. The exact recipe varies by product and manufacturer. A discarded tire contains several valuable material streams. The rubber can become a secondary raw material. Steel reinforcement can be recovered for metal recycling, while textile fibers can be separated from the rubber fraction. Modern tire recycling is therefore not simply about cutting tires apart. It is about recovering as much usable material as the process can efficiently separate. The process begins outside the factory. End-of-life tires arrive from collection networks, vehicle service locations, and other authorized sources. Before they can enter the machinery, they are treated as a raw material stream that must be controlled, inspected, and documented. Moving tires efficiently matters because the recycling line can only operate when its feedstock keeps arriving. At a large facility, logistics becomes part of the manufacturing system itself. Trucks deliver the tires, unloading equipment transfers them inside, and conveyors eventually take over the movement. At the receiving point, incoming loads can be weighed and recorded before processing. This gives the plant a basic material balance: how much feedstock arrived, how much enters each processing stage, and how much material eventually leaves as recovered rubber, steel, fiber, or other outputs. Not every tire entering the facility looks the same. Passenger tires, truck tires, and heavily damaged casings can differ in size, construction, and reinforcement. Operators inspect the incoming stream and remove unsuitable objects before the cutting equipment begins. Good sorting protects the machinery and keeps the recycled material more consistent. Before the first major cutting stage, loose debris and obvious contaminants are removed. The objective is simple: present the shredder with a controlled feed of tires rather than a random mixture of materials. This reduces interruptions and helps maintain a predictable processing rate. Now the real transformation begins. The whole tire enters a primary shredder, where powerful counterrotating cutters tear and shear the rubber structure apart. The first objective is not to create tiny particles. It is to reduce the tire to manageable pieces that can be processed again. Primary tire shredding commonly produces much larger pieces than final crumb rubber, with subsequent stages responsible for further size reduction. The shredded pieces are still too large for precision rubber processing. A secondary reduction stage cuts them again, producing smaller and more manageable pieces. The exact particle size depends on the equipment and the final application, but the principle remains the same. Controlled size reduction makes later separation and grinding more effective. Inside a tire, steel reinforcement gives the structure strength. After shredding, much of that steel becomes exposed. Powerful magnetic separation systems can capture ferrous wire and metal fragments from the moving rubber stream. Multiple separation passes may be used to improve recovery and rubber purity.